So now, for a while, I will forget about the problem and introduce this story of normal coordinates and normal forms in Sub-Riemannian geometry. And as a first step, I will do it for corank 1 distributions. First, corank 1 distribution. Then, so I have my manifold n dimensional. So, and then I have, let me say maybe n plus 1 that dimensional, since I shall consider corank 1 distribution. Then my Sub-Riemannian metric is specified by a control system or by the setting of n vector fields that are orthonormal frame for the distribution. And in fact, what I will define is normal coordinates with respect to non-admissible curve gamma. Then I am also given the Sub-Riemannian metric, but I am also given the curve gamma and the gamma is everywhere transversal to distribution. Okay? I assume this. Then, okay. Then I choose, this is local, it is a concept which is local around gamma, in a neighborhood of gamma. And there is a coordinate system local around gamma, which first it rectifies gamma, so that gamma dot is ddx n plus 1. Gamma dot is the vertical axis, and I choose coordinates are like that. I require this. I require that gamma is in fact the curve gamma of t is in fact the curve 0, 0 t. Okay, no more than that. I require that the distribution at gamma of t is just d dx1 d dxn, the horizontal planes. This is possible clearly, and I require that so I have to define now what is the T epsilon is a Sub-Riemannian tube, SR tube of radius epsilon along gamma, and C epsilon is the same, but the boundary of the tube, just the cylinder. Okay, and first, well, I say what I require after we discuss. There is this, and what I want also is that, of course, the metric G along gamma of t is the standard Riemannian metric, is the standard Euclidean metric. And I require also in these coordinates that C epsilon, the cylinder or radius epsilon, is just the usual Riemannian cylinder. So it is just a set of x such that x1 square plus x1 square is equal to epsilon square. I require this. And the first thing that has to be clear is that such coordinates do exist. They do exist due to the fact that the curve gamma is assumed to be transversal to the distribution. And Andre, maybe because I never thought about the case where, well, I thought, but very little, you know, the case where the non-admissible curve has extraordinary points where it is tangent to distribution. By the way, this is generic in R3 for contact distribution. At isolated points, the fact that the curve is tangent to distribution is generic situation. Only in dimension 3, but and in that case, for me, it is not a problem because it is points where the curve is almost is locally admissible. Then it doesn't make any problem, and it doesn't pose any question in my case. But nevertheless, how is the
normal form? You mean what is the normal form?
What is the shape of the cylinder? How it is and what? And I thought about that just this morning when walking to the lake. But I am not completely sure that what I will say is true about that. But you will tell me. It seems to me that in that case, so you have a curve which is tangent to the distribution at a certain isolated point. Then the cylinder should be like that. It is a sausage around the curve. If the curve was transversal to the distribution, it is clear that the cylinder is the usual smooth cylinder. But here, it must be a sausage, but if you look from below, there is a cut locus like that. There is a non-smooth, here is the tube. If you look from below, there is a non-smooth segment like that. And look, and if you think about, okay, what is quite clear is that okay, the variables are x1, xn, and xn plus 1, and in cotangent space, dual variables are p1, pn plus 1, and we are interested with we have a quadratic Hamiltonian px1 square plus etc. plus px1 xn square. We have this Hamiltonian H, and we have Lagrangian manifold, which is x1 to xn equals 0, and pn equals 0. this is Lagrangian manifold, yes?
But this is maybe to explain to people why you consider this Hamiltonian. So it's
I explain oh, okay, sorry. But it seems to me that the wavefront corresponding to this Lagrangian manifold, the wavefront and the...
But that you know, that lecture is not for me. You should.
Okay.
What is the PX1? PX1 in Hamiltonian.
Okay, so but the point is that this is a bit something to I was thinking about this morning with no and as I told you, these points are of have no importance in my
they do not contribute because the length is finite. When you approximate it,
yeah,
it's finite.
they do not contribute at all. But anyway, it is an interesting question.
Sure.
And it seems to me that, okay, if you look at this story of normal form is in the appendix of my notes. It is a paper with Andrea Gratchov. And on this paper at the end, you can see the singularities that happen for the Sub-Riemannian balls. And it seems to me that the singularity and the Cutler-Locus wavefront and conjugate locus. And it seems to me that that they are exactly the same. It is Cutler-Locus should be a line.
Jean-Paul, this is not this is we may discuss, have a lot of time to discuss.
So I have to, but okay.
Go to your lecture.
But do you agree?
I'm not sure, no, let's go to your lecture.
Okay. So not only I claim this, that it is non-smooth, but it is non-smooth even if the distribution is not one-step bracket generating. It is, so, even the picture should be the same. But okay, we discuss that after. I have to forget about you. So. Then, such coordinates do exist, and these cylinders actually are smooth cylinders. These are smooth coordinates due to the fact that the curve gamma is transversal to distribution. So, these are the normal coordinates with respect to gamma. And now I have to, you know, it is very important in this elementary Sub-Riemannian geometry. As soon as you start to compute geodesics of the metric and so on, there are two ways. Either you do it completely intrinsically, like does Andrea Gratchov using his chronological calculus and so on, or you do it like an engineer, like me, and you try to construct nice normal forms. And it turned out that this normal form that were already, by the way, introduced, I don't know if I am right, but the equivalent of these normal coordinates and the normal form were you find them in the book of Darboux first for Riemannian surface, dimension 2 Riemannian surfaces. And in these normal coordinates, curvature appears. Curvature at the point appears very, very natural. Okay?
But is it true that boundary of this tube will be, which consists as union of all exponent ball, Sub-Riemannian ball?
It is. Yes, it is true, but it is not in this detail really. Just think about it. You will see that due to this, due to this transversality. But I can explain. But if I explain, it takes half an hour. Maybe it is not necessary. Okay. But believe me, it is true that as soon as the curve gamma is transversal to distribution, the Sub-Riemannian cylinder is smooth, even if the distribution has singularity, as Martinez singularity or something like that. it works. Then now you have this normal coordinate. I shall construct a normal form for my.
But in this case, you cannot assume that all normal geodesic, in horizontal geodesic starting from point of your cap will be written as bilinear equation. This you cannot achieve, yes?
Sorry, I cannot.
So if you consider, you have point of your cap and you consider geodesic in horizontal direction.
You have the curve gamma which is vertical, let us do it in R3, okay, you have two coordinates x1 and x2, and
admission geodesic will
the
be
curve gamma is here, the geodesics that realize the minimum distance between a point sufficiently close to this curve is exactly perpendicular.
Yes, but you cannot write that will be some linear equation like in Riemannian geometry. If you have normal coordinates, then your geodesic starting from a fixed point will be linear, given by tx. But in this case, you cannot do it. Yes, because
I will do it immediately.
No, but because you have conjugated point for any small epsilon, so you cannot use a real normal
Not
coordinate.
here. Not here.
No.
I do not have conjugate point for this. You have conjugate points.
So you say that
you have conjugate points for geodesics starting from a fixed point that realize minimum distance. I consider geodesics that realize minimum distance from a point to the curve gamma.
So in fact,
I just kill
Fermat geodesic, not coordinates.
I kill the conjugate points. It kills the conjugate
So in this case will be no conjugated point along K.
Along.
Understand. So
Exactly.
so it's canonically defined up to some.
And now let me construct a very specific normal form for the n tuple of vector fields that defines the distribution. Then I have coordinates, these normal coordinates. So let me split them, these coordinates. I will call Z and W. Z is the horizontal coordinates x1, xn, and W, well is the vertical coordinate along gamma. Okay.
But I think most appropriate name is Fermat coordinate, because it's exactly Fermat coordinate in general relativity. Along any cap, you can do it.
And then you, I write. This is, if I put, now I can work in coordinates. Then I can consider matrices. Then X is this matrix, exactly. I put x1, x2, xn close. And in fact, so this is X. And in fact, I can write this matrix like that, X. Formally is Q, to be short, Q ddz plus N ddw. Q. Okay. Just easy. Just the variable z are the first, and this is square matrix. And in fact, due to the fact that they are I am working in normal coordinates, and then what is clear is that Q along gamma is equal to the identity. It must be like that, due to the fact that Q is a metric, and due to my construction of the normal coordinates. Q along gamma is the identity. But maybe Q along gamma is not at least, so Q is a square matrix, but it is clear now that I can choose it, I can choose Q symmetric. Why I can choose Q symmetric? I can choose Q symmetric because Q I can factor smoothly by using polar decomposition into the product of a symmetric matrix times orthogonal 1. Yes? H is orthogonal. Okay? And now, what is this? So this orthogonal matrix is a rotation matrix. I use this rotation to rotate my orthonormal frame. If I rotate orthonormal frame with H, I rotate, it doesn't change the metric. Then, in fact, assuming that Q is symmetric, it's just changing the orthonormal frame by certain rotation. Okay, I can choose Q symmetric, and almost unitely, it remains a single degree of freedom that maybe you do not see immediately, but that you will see in a minute. But whatever this degree of freedom, what I shall say now will hold. I claim that in normal coordinates, the following properties hold. I claim that, so Q is a function of the point, x. Okay? It satisfies the following. It satisfies Q of x times x. Q is symmetric matrix. This is x is vector. Times z equals z. Z is the first n coordinate. Okay. I claim that these two equalities are, and in fact L of x times z equals 0. And this defines completely the, conversely, if these properties are true, you are in coordinates are normal with respect to the vertical coordinate. Let us prove this. So to prove this, I shall use the maximum principle. I don't think it is necessary to recall anything about maximum principle, no?
It might be better to recall briefly.
At this point. Okay.
Well, just for this case.
Okay. Well, I shall try to recall very few. Maximum principle in that case tells you that these geodesics here that realize the minimum distance to the curve, these geodesics are trajectories of the following Hamiltonian system. Sum of the. I consider this Hamiltonian. H equals sum 1 to n pxi square. Maybe I put 1/2. I put 1/2 for normalization reasons. Then I have trajectories. This is Hamiltonian. Then you have trajectories.
P
is dual variable to x.
But it is a momentum.
It is. I am in coordinates, okay?
Yeah.
Then the p's are dual coordinates.
Yeah, but with some indices we have n dual. And what is p without indices?
P
No, it's a scalar product. It's
X,
not clear that
xi is a vector.
It is
And
dot, it is scalar product.
It's not scalar product because P is cotangent vector. So this evaluates
okay.
on-
Okay.
P is a
Pa-
row,
pairing,
the next
standard
one is
pairing,
the-
I understand.
Yeah.
it's a column.
So P is vector.
P is form,
One form, yes, of course.
one form.
So P is element of
Element of
cotangent
cotangent bond evaluated or I consider trajectory and such that I consider trajectories of this Hamiltonian system that start from gamma. Okay, I consider curves x of t that are trajectories of this Hamiltonian system and that start from gamma. That it means that x of 0 is a certain gamma of s. Okay? I consider trajectory of this Hamiltonian system and such that p n plus 1 at time 0 is equal to 0. These are the Pontryagins for those who know maximum principle. It is transversality conditions with respect to the vertical line. Then Pontryagins maximum principle is a variational principle that tells me, in that case, that these trajectories, these horizontal trajectories, are trajectories of this Hamiltonian that satisfies this boundary condition. Is it enough? Then you have this. Some variational principle tells you this, that these trajectories, these horizontal trajectories are like that. Okay. Now, what also Pontryagins maximum principle, this variational principle tells you, unfortunately it is not enough, it tells you that these trajectories are x of t or x of t it tells us that p of t is transversal to ct. At time t, the vector p at time t vanishes on the tangent to the cylinder. It is this in control term is just the fact that in the Pontryagins maximum principle, the adjoint vector is transversal to the accessibility sets. It is this.
It is analog of Gauss-Lemma.
Yes, something like that. Then P of t is transversal to this cylinder that are smooth. And now I just write this. I write that P of t is transversal to Ct. I write it in coordinates. It is a small computation, very, very interesting, but not too complicated. Okay. Then since P of t is transversal to Ct, it is clear that P of t is equal to a certain mu of t z dot of z is this trajectory. Then it is clear also, by the way, that not only Pn plus 1 of 0 is 0, but also Pn plus 1 of t is 0. Let's use it. Because you have to be orthogonal to this circle. And if you want your geodesics to be straight line, they have to be collinear to this vector. Has to be collinear to velocity, this vector, if you want it to be velocity. Then P is equal to mu z dot. Sorry, not P, but P transpose, because P was in cotangent bundle. So, and I am working in coordinates. And if I want to write vector, I have to consider P transpose of mu of t, z dot of t, and also this is equal to mu of t q sorry. PQ. This is due to the fact that in fact this Hamiltonian, in my abbreviated notation, this Hamiltonian H is 1/2 of PQ PQ transpose. This Hamiltonian, in my abbreviated notations, is just this, okay? It is like that. And then I have that P transpose is equal to mu z dot, mu q PQ transpose, sorry, and then PP transpose, which is a scalar, and in fact which is and this PQ transpose is equal to mu PQ transpose, like that, and but this is equal to this is equal to mu. Why? Because I took you can choose a level set of for the Hamiltonian. Hamiltonian is constant, and then I consider the level set 1/2 of the Hamiltonian, which means that PQ times PQ transpose is equal to 1, by the way. Okay? So PQ transpose is equal to 1, then this is equal to mu, then this is equal also to, this is equal also to mu square norm of z dot square y. Why? Why this? Okay, just because, okay, P transpose, okay, P transpose is equal to mu z dot, and if you multiply by P, apply it twice, you get that it is mu square norm z dot square, but this guy must be equal to 1, because this assumption that the Hamiltonian is 1/2 means that the geodesics are parameterized by arc lengths. And then you have that mu is equal to mu square, and then mu must be equal to 1, because mu cannot be non-zero, by the way. If mu is 0, since r is 0 also, it would contradict maximum principle. Then this mu is equal to 1. Okay? This mu is equal to 1. And then, now it is almost finished, because what we have is that we have the following. So P transpose over mu is equal to Z dot is equal to Q square P transpose, because Q is symmetric. Now this mu is equal to 1. Okay? So this is P transpose. Okay? But also you have the following. You have also that lambda P, that P transpose is equal to Z. You have this also. Because if the geodesics are straight line, velocity, not only so Z dot is in the same direction of Z. The only thing is that lambda at 0 is 0 now, although mu was always different from 0, but here lambda at 0 is 0, but at other time it is non-zero, 14 non-zero. Then you have this also, and then if you apply this, just this, what you get? You get that Z is equal to Q square Z. Just here, because mu is equal to 1. And if you apply this, and Q square, because Q is symmetric, then you get this. Z is equal to Q square Z, which means that Q square, which means that identity minus Q square Z is equal to 0, which is identity plus Q identity minus Q Z is equal to 0. But this guy must be invertible, because Q is a Riemannian metric. Q is positive. In fact, Q at 0 is identity, moreover. Then this implies that high minus QZ is equal to 0, and then QZ equals Z, what I wanted to show. It is what I wanted to show. It is what I wanted to show. And similar reasoning to this, all this is written in the appendix of the notes that you give to the participants. It is a part of an old paper with André. Okay, then you have this. And with a similar reasoning, very similar reasoning, you get that LZ is equal to 0, using properties of Contré-Huygens. Contré-Huygens maximum principle is very efficient. And then, this is the, so, and converse all everything. And to summarize, if you are in normal coordinates, and if you have chosen Q to be symmetric, then you have Q times Z is equal to Z, and L times Z is equal to 0. And conversely, if you have a symmetric Q, oh sorry, it is finished. It is a pity, because I was on the point to show to prove the Sub-Riemannian Bianchi identity. That is that all what I said is valid in Riemannian geometry. And as you know, if you expand this Q in Riemannian geometry, if you expand this Q, first order term is 0 term is 1, and first order term is 0. This is the Bianchi identity. So I will prove the same, and you will get the Sub-Riemannian Bianchi identity. And I am almost at the normal form in the current quantity. Okay, sorry, but in fact it is, I have to say much more, to give much more details than what I expected.
Okay. Give you more time.
The first